On a circle of unit radius, pick a chord uniformly at random. What is the probability its length is greater than square root of 3? Let's make it a multiple choice question. Your options are 1 by 2, 1 by 3 and 1 by 4. Pause the video and see if you can solve the problem. The surprising fact is all the three answers are correct. This is a paradox discovered by the French mathematician Joseph Bertrand. I will explain the details later. First, let's compute these three different values. To see why 1/2 is the correct answer, imagine a unit circle centered at O. Draw a chord AB of length square root of 3 and then draw a line OD passing through midpoint C of the chord AB. Since AB equals root 3, AC equals root 3 over 2. From basic geometry, we know line OC is also perpendicular to the chord AB. Applying the Pythagoras theorem to triangle OAC, we find that OC equals 1/2. Here's the result. If the perpendicular distance of a chord from the center of a unit circle is greater than 1/2, then the chord length will be less than root 3. Otherwise, it will be greater than root 3. So, the probability that a random chord is longer than root 3 is simply the ratio of length OC over length OD, which comes out to 1/2. Now let's understand why 1/3 is also a correct answer. Once again, take a unit circle with chord AB of length square root of 3. From the center O, draw lines to the endpoint A and B. Using trigonometry, we can calculate the smaller of the two central angle AOB. Since OC equals 1/2 and OA equals 1, the angle comes out to 2 times inverse cosine of 1/2, which is 120 degrees. Here's the result. If a chord on a unit circle makes a central angle less than 120 degrees, its length will be less than root 3. Otherwise, its length will be greater than root 3. Therefore, the probability that a random chord is longer than root 3 is 180 minus 120 divided by 180. This results in 1/3. Finally, let's see why 1/4 is also a correct answer. Start with a unit circle and a chord AB of length square root 3. Draw a line from O through C. We already know that OC equals 1/2. Now, draw a smaller circle centered at O with radius 1/2. Here's the result. A chord on a unit circle will be shorter than root 3 if its midpoint lies outside the smaller circle. Otherwise, it will be larger than root 3. This means the probability is simply the ratio of two areas, the area of a small circle to the area of big circle. The small circle has an area pi times 1/2 squared, and the big circle has area pi 1 squared. On division, pi cancels out, leaving 1/4 as the solution. So why do we end up with so many answers to the same problem? As mentioned earlier, this is known as Bertrand Paradox. In classical probability theory, when we deal with simple cases like rolling a die or tossing a coin, we rely on intuition and prior experiences to define equally likely events. But with random chord on a circle, the situation is different. The sample space of all possible chords can be described in several ways: by their perpendicular distance from the center, by the central angle they subtend, or by the position of their midpoint. Each way gives a different meaning to the word uniform and yields different probability. The axiomatic probability framework fixes this by requiring specification of a measure which precisely defines how probability is distributed over the entire sample space.